Okay, now I'll just explain a bit about the basics of capacitance from last week, just so we can look at the bigger picture now. Now, if you recall what I mentioned about capacitors, if you want to charge your capacitor, which is this component here, must be connected to a voltage supply in order for it to be charged. So when you connect a capacitor to a voltage supply in order for it to charge up, what actually happens is that you will have an amount of charge, or rather you would have a group of electrons that are actually being pushed from the negative terminal of your battery towards one plate of your capacitor. But that charge cannot actually pass through your capacitor because there is a layer of dielectric in between. So what happens then is that that amount of charge, negative Q, actually gets deposited on one plate of your capacitor, causing that plate to acquire a negative charge. Okay, that plate acquires a charge of negative Q because the amount of charge that has been deposited on it is negative Q. All right, but at the same time, what then happens is that that same amount of charge of negative Q is now going to be repelled off the other plate so that it moves like this towards the positive terminal of your voltage supply. Now, because this other plate here has already lost an amount of charge of negative Q, it causes it to acquire a positive charge now. So this plate here now becomes positively charged, and the charge that it acquires is positive Q. Because it lost negative Q, it therefore must acquire a charge of positive Q. Okay, so this is what the first statement here written is telling you about. An amount of charge negative Q is pushed to one plate of the capacitor, and then the same amount of charge is repelled off the other plate. It causes both plates to acquire an equal but opposite charge. Okay, but when you look at it as a whole, you look at the entire capacitor, what you could not say is that it does not store charge. Okay, because there's no net change in the charge of your capacitor overall here. All right. So does that mean the other plate already has charge? Yes, correct. Both plates actually have a charge now, just that they are having opposite signs of charge. Initially, they do not have any charge because if you think about it, when the capacitor isn't charged, both plates actually have no charge. There's no charge on the right plate, there's no charge on the left plate. So your net charge here is definitely going to be 0. But when you try to charge it by connecting it to a voltage supply, it causes one plate to acquire a negative charge and then the other plate to acquire a positive charge. But the magnitude of your charge would be the same, although they are opposite sides, okay? Because you're having amount of charge of negative Q here, it's like this. If you have an amount of electrons here, here also has an amount of electrons. The more your electrons are deposited here, it's going to cause a greater repulsion on the other electrons on the other side here. So these electrons will be repelled off the other plate. Because here, you are pushing an amount of negative charge. Here also, you have the electrons here. Because this plate has become negatively charged, the electrons on this other side must also be pushed off. Okay? So it happens when you push an amount of charge on one plate, then the other plate must have an equal amount of charge being repelled off. It's like you push one electron here, another electron here must be pushed off. Okay, so you must have charge being repelled off the other plate for your capacitor here. All right, because your parallel plate is actually made out of a metal conductor. You have mobile charge carriers, usually in the form of electrons. So if you already have a group of electrons deposited on one plate, because of the close proximity of that plate to the other plate, it causes electrons on the other side to be repelled off also. Okay, so here, once you have an amount of charge that has been pushed to this side, you have an equal amount of charge being pushed off the other side. Okay, so that causes these two plates to acquire an equal opposite charge. All right, your charges here are actually made out of a group of electrons. Okay, but to make your analysis simpler, I just say an amount of charge of Q lah. Okay, so there is an equal and opposite charge on each plate. So if you try to add up the net charges, like the ones that you're seeing right over here, if I say that the right plate has a charge of negative Q and the left plate has a charge of positive Q. If I were to add up their charges, their net charge is actually Q plus negative Q equals to 0. So if you compare the capacitors before you charge it and after you charge it, there's actually really no net change in your charge. So you cannot just simply say that there is actually charge being stored in your capacitor. Okay, what has actually happened is that there's charge separation, because you see initially there's no charge on either plates. Now suddenly there's a positive charge on the left plate and a negative charge on the left plate. This is what we call by charge separation. And your charge separation here is what actually causes you to have energy stored inside a capacitor, because if you recall how your capacitor works, you're trying to push negative Q here, and then you're trying to push off negative Q here. So the negative Q here is actually made out of electrons. You're trying to push electrons to one plate, and then you're trying to push electrons off the other plate. This requires work to be done. Okay, so that work done is actually stored as energy of your capacitor. Okay, so here, the main thing to know is that overall, when you're talking about a capacitor, it doesn't store charge because there's no net charge stored. Instead, there is charge separation. Okay, but it somehow will give you the false impression that charge is seemingly stored. Why do we say that? It's because if you have that same fully charged capacitor that you fully charge, you go and try and connect it to a filament lamp or any other lamp. So you look at the diagram on the left, your capacitor is charged with a certain amount of charge. This one is positive, this one is negative. So earlier, it was already mentioned that your capacitor, this plate has a charge of negative Q, this plate has a charge of positive Q. So once you connect it to a lamp, your capacitor will now try to discharge. So that charge of negative Q that you originally deposit here will now try to move through the other plate. It will now move through your circuit to the other plate. So it will move from this side, flowing through your lamp, causing it to light up, and then after that it will keep on moving until it reaches your other plate. And once it reaches the other plate, because this is positive, this is negative, the plate will discharge. Okay, so here, because your lamp suddenly lighted up, it gave you the impression that there must be, because your lamp lights up, there's current flow, there's charge flow, so the charge must therefore come from the capacitor, isn't it? So it gives you this false impression that charge was actually stored by your capacitor when it isn't. Okay, here, if I wanted to word it, I would probably just say that charge is stored on each plate, and during discharge, charge on one plate is actually released so that it flows through the circuit to the other plate in order to discharge it. Okay, this is the reason why you have that false impression that the capacitor stores charge. Whatever charge you originally had here was actually being released so that it flows through the circuit to go back to the other plate and discharging it. Okay, that's why people always think from this example that your capacitor is actually storing charge. It isn't storing charge. What it did was that it actually separated the charge, and then because it separated the charge, negative charge were always on one side, positive charges were always on the other side, so that when you want to discharge it, whatever charge you had originally on one plate is actually being released to go back to the other side. Okay, so this is what we mean by your capacitor storing charge here. Okay, now then when you're talking about the equation C equals to QV for definition of capacitance, that Q there, we often call it your charge stored. The charge stored here is actually only on one plate of your capacitor only. Okay, so that's just one thing to take note of. Whenever you want to use the equation C equals to Q over V, that Q is actually the charge stored on only one plate of your capacitor. All right, so that one hopefully is clear. And in some of the older past year questions, they will somehow ask you, why is it that your capacitor, why is it that when your capacitor is connected to your circuit, current can still flow through your circuit, The main thing to know here is that current does not actually flow through your capacitor because there's a layer of dielectric in between, but current does actually flow through other parts of your circuit because of the pushing and repulsion of charge or electrons off the plates. This one I probably forgot to write this. Because of the pushing and repulsion of charge off the plates. Because if you look at the diagram on the left, the first part, when you're trying to charge out your capacitor, you can see that negative charge of negative Q is flowing like this, but then it stops here. And then after that, on the other plate, an amount of charge of negative Q gets repelled off and it flows back to your positive terminal here. So at these two parts, there is current flow, but there's no current flow through your capacitor. Okay, the reason why you have current flow through your circuit was because of the repulsion and pushing of charge to your plates. That's how your current came about. Even when you're talking about discharging your capacitor, it's actually the same thing. When you're trying to discharge your capacitor, the charge negative Q flowed from here all the way to here and then back to the other plate. So there is charge flow, so there's current flow in this loop, but it just doesn't flow through your capacitor. Okay, so current can flow, but just not through your capacitor. And that origin of your current flow is due to the repulsion and pushing of your charge to the plates. Okay, so that is the basics of that. All right, so maybe we just do some questions so that whatever we discuss is easier to digest. Okay, you guys can have a look at page 73 first. Yeah, we'll just do the short explanation question at the beginning. Yeah, we can't do the calculation first because this one is a bit more difficult than the usual question. Right, so if you look at that particular question on page 73, two flat metal plates that are held a small distance apart by means of insulating pads as shown in this figure. Explain how the plates could act as a conductor. Okay, so that's what they want you to do. This one, let me just open up the past here. I just closed it off just now. June 2021 P41. So how would you explain that two plates acting as a capacitor? Wait, am I in the correct year? Oh, June 2021 P42, sorry. So how would you explain that this plate can act as a capacitor, right? So what you remember just now when I explained to you the capacitor was that you always need to have two parallel metal plates, which is separated by a layer of insulator, such that when you connect it across a voltage supply, say like this one, you will have a certain amount of charge caused by your electrons that tries to move towards this plate and gets deposited here, so that this plate becomes negative Q. And then likewise, you would have a similar charge, negative Q, being repelled away from the other plate, which causes this plate to become positive Q. Okay, that was how your capacitor became fully charged. And then that was how you ended up getting charge separation. Okay, so right now, when you look at your current diagram, this is actually quite similar to this in the sense that you have two metal plates, top and bottom here, and then in the middle is really just air. Okay, there's an insulating pad, and then after that, there's a layer of air in between, right? Because they're not in contact, there's a layer of air in between. This is actually something like your insulator, like your dielectric insulator. So structure-wise, this is similar to your parallel plate capacitor. Okay, so how would it act as a capacitor? You would word your answer in a manner similar to this. Okay, you would just say that if you were to apply a potential difference between the plates, it causes charge separation between the plates, like this situation here. Okay, Or another different choice of answer that you can use is that you will probably say that a potential difference applied across the plates will cause energy to be stored between the plates. It's actually the same thing. It's because you have charge separation that you have energy stored in the first place. Okay, right? So this is for this part. This is page 73. Part B, this one we will revisit it at a later time next week. Okay, because I just need to go through the state and explain part first that deals with how a capacitor works. Okay, if 73 is okay, you can have a look at page 28. This is also the other one that you need to go through later on. Okay, it's June 17 P42. Right, so here we'll have a capacitor that consists of two parallel metal plates that is separated by insulator as shown. Suggest why when the capacitor is connected across the terminals of a battery, why is it that when you go and connect this to the terminals of a battery like this, the capacitor is actually storing energy but not charge? Okay, so this one is something that I explained just now in the notes. You will say something like this, where there are equal opposite charges on the plates, so there's no resultant charge. When we say equal opposite charge, it's referring to this and this. You see, you go and push a charge of negative Q towards the right plate here, causing this plate to become negative Q. But after that, you repel a same charge, negative Q away, causing this plate to become positive Q. So the charges here that you see are actually equal and opposite. You see this one here is your charge separation. But at the same time, you can see that this one is positive Q, this one is negative Q. They are equal opposite charges. Okay, so this one, if anything, maybe I just write this now. This one, you have equal but opposite charges. Therefore, net charge equals 0. Okay, so if anything, is there anything else I need to add here? No need. Okay, so here you can just say that there are equal opposite charges on the plate, so there's no resultant charge. Okay, that's why you cannot say it's storing charge. And then after that, how do you explain the part where you have energy stored? You could actually say this. When you try to separate the positive and negative charges, you are actually doing work, so energy must be stored here. Okay, so this one is what you can actually say here. All right. So is there anything here I can actually write? Maybe I should write it as this. Just give me a moment. This one, let me redraw the diagram. Maybe this one will be better. This one is equal but opposite charges. Therefore, net charge is 0. And then after that, if anything, I can probably just say this one here, this one here, and this one here is your charge separation. Okay, yeah, this diagram looks better now. Okay, so part A is okay. Then you look at part B, define the capacitance of the capacitor. Okay, they're asking you to define the capacitance of the capacitor. Your capacitor here is your parallel plate capacitor. So the definition that you use needs to be a bit more specific. Okay, and that's the reason why it's also worth 2 marks here. So for the capacitance of a parallel plate capacitor is actually just the charge stored on either plate of your capacitor per unit PD applied across the plates of your capacitor. This one is actually the definition from your notes under page 3. Okay, there's 2 definitions that I gave in the beginning. One for a general definition, one for parallel plate capacitor. So you use the definition for parallel plate capacitor. Okay, so that one should be okay. And then another thing that you can do is part C. Now in part C, your capacitor is, okay, maybe I should just zoom in. Okay, now for part C, your capacitor is charged so that the potential difference between its plates is V naught. That capacitor is then connected across a resistor for a short time. It is then disconnected. The energy stored in the capacitor is reduced to 1/16 of its original value. From here, determine in terms of V naught the potential difference across your capacitor now. Okay, so what you have is a capacitor that was connected across a fixed resistor like this. Okay, so what happened then was that when you go and connect your capacitor across a fixed resistor, it will start to discharge through your resistor like this. Probably negative Q comes out and then tries to flow over to this side here. Okay, so in the process of it flowing from this side towards this side, you would have charge flowing, you have current flowing, you have energy being dissipated through your resistor. So at the end of it, they say that they suddenly disconnected your capacitor and the energy stored inside your capacitor is 1/16 of its original value. So what's the new PD across your capacitor right now? Okay, so what we do know is this. When you try to discharge your capacitor, your E2 is actually now 1/16 of E1. Okay, so this is what we know. All right, so in you're talking about energy of a capacitor, we know that E is half CV squared, E is half QV, E is half Q squared over C. Okay, so when it comes to energy, I have these three choices of equation to use, but which one is actually a more suitable one for you to use? The more suitable one is actually the first one. The second one and the third one will not be suitable. Okay, so if you look at the second equation, you want to find the V, but at the same time, you also do not know what is the charge stored. So you have two unknowns. This one is definitely out. And then after that, if you look at the third equation, you do not know what is the charge. And then your capacitance here, although you do not know them, what you do know is that the capacitance value is fixed or constant. Okay, so although you can get some sort of relation here, it's not answering the question because you want the potential difference, you want the V. So the third equation is also out. Okay, so the only suitable one is going to be the first equation here, because this V here is what you want to find. And then when you're talking about capacitance value, remember just now I told you, regardless of whatever PD or charge that is stored inside a capacitor, the capacitance value itself remains fixed or constant. So this one is fixed, or you can also call it as constant. So I want to use something like ratio here, where I say that E is half CV squared before I connect the capacitor and after I connect the capacitor. The capacitance value itself remains fixed, is constant, so E is proportional to V squared, such that E2 to E1 is V2 squared to V1 squared. So remember just now I told you E2 is actually 1/16 of E1. So you can actually just say 1 over 16E 1 over E1 is equals to V2 squared over V0 squared. Your V1 is already known. They already told you when the capacitor is fully charged, the PD between the plates is V0. So V1 you already know is actually just V0. Okay, so I put it as V0 squared here because it's V1 squared. Right? So you try to solve this equation, eventually you will get the answer as V0 over 4. Okay, this is the new PD on your capacitor right now after it has discharged some of its energy away. Okay, so just remember this. When you do your ratio questions, usually you try to pick the one with capacitance inside because the capacitance is always fixed, right? That's the reason why just now I kept mentioning to you that point is important, okay? Because if you use the other equations, you will notice that you either have two variables or you end up with something that is not what the question wanted. Okay, so this one is page 28. This one is done. Next one you can have a look at is probably page 49. Okay, so have a look at page 49. Right, state two different functions of capacitors in electrical circuits. What do they do when you connect them inside electrical circuit? You can actually make use of any of the answers that I wrote on the first page. To separate charge, to store energy, or to smoothen and rectify AC, you can actually just choose either one of them. Okay, so here you can just say is to store electrical energy or to smoothen ripple on direct voltages or current. This is actually the part where you say, this is actually the same as you saying smoothen, rectify AC, smoothen, rectify alternating current. This is actually the same thing, okay? So there are also other answer choices here, but they are not really that suitable for you to use. Okay, here you say this marking scheme says your capacitor is used for timing delay circuits, in oscillator circuits, in tuning circuits to prevent arcing or sparks. This one I won't use this now, right? Because if you just write this, you don't even understand why is it like that. So don't use this answer. You just use the first two. That one should be okay already because you will directly learn this in your syllabus. Okay. There's also another possible answer that you can use. That one is to block direct current. Okay. Your capacitor can be used to block direct current. So how does it block direct current is through a manner like this. Remember just now when you try to connect your uncharged capacitor to a power supply, like this one, initially there's electron flow like this and like this, but once your capacitor becomes fully charged, your electron flow will just stop completely, right? So when you have no electron flow, you have no current flow. That's what we mean by blocking direct current. Okay, when you put your capacitor initially in between, current may still flow a little, but after that it will stop. Okay, so this is what we mean by blocking direct current. This is another answer that you could use. Okay, then let me just clear this thing off. Okay, then if you look at part B, right over here, you have three uncharged capacitors or capacitances C1, C2, C3 connected in series with a battery of EMF E and the switch as shown. When the switch is closed, there is a charge positive Q on plate P on the capacitor capacitance C1. So this is plate P, you have a charge of positive Q here. Show that the combined capacitance of the three capacitors is given by this expression here. This is actually just asking you to derive an expression for capacitances in series. Okay, so if you recall what I mentioned earlier, you need to relate to your Kirchhoff's first and second law. If you look at Kirchhoff's second law first, this one is V1, V2, V3. Applying Kirchhoff's second law would tell you that E is equals to V1 plus V2 plus V3. And then since C is Q over V, V is Q over C, you sub it in, you're going to get Qt over C equals to Q1 over C1 plus Q2 over C2 plus Q3 over C3. Okay. And then after that, recall also that if you try to push a charge through your series circuit, it could be that you have a charge of positive Q coming in like this. You'll really just be a charge of Q stored in each capacitor. Okay, because what you actually push through your circuit is Q. Whatever charge is stored in your capacitor is really just Q itself. Okay, so you can actually just say that Qt is equals to Q1, Q2, Q3, or just positive Q lah. This positive Q is actually from here. All right. If you, maybe I try to redraw this so that it's easier for you to see. Just give me a moment. I'll try to relate to what your questions say here. If this one here is positive Q, your plate here will be positive Q. This one will be negative Q. Because if your positive Q is stored here, that means a charge of positive Q has come to this plate, causing another charge of positive Q to be repelled away. So when the charge of positive Q is repelled away, this plate here becomes negative Q to be exact. And then when the negative Q here is pushed to the second capacitor, it gets deposited here, causing this plate to become positive Q. And then the same positive Q is repelled away, causing the other plate to become negative Q. So again, you can see that the process will repeat itself until eventually you see a charge of Q coming here. Okay, so this plate here will be positive Q, negative Q2. Okay, so over this side, because you have a charge of Q deposited here, you can also imagine that whatever came out of your battery in the first place was really just positive Q. Okay, so to make things short, if you see is the charge Q being pushed out your battery or cell, it's just going to be that same charge on your capacitor itself because they're connected in series without having to look at these things like this. You look at these things like this, is going to waste a lot of time just to understand it. Okay, so the shortcut will be just to see that whatever charge is pushed out of your battery or cell, that one will be the charge stored on your capacitor itself, on one plate of the capacitor itself. Okay, so here Q1, Q2, Q3 is just Q. Substitute into your equation. You notice that you can cancel them off eventually, giving you 1 over C equals to 1 over C1 plus 1 over C2 plus 1 over C3. Okay, so this one is your derivation for capacitors in series. Okay, then next one. This one here is a student has 4 capacitors, each of capacitance 20 microfarad. Draw circuit diagrams, one in each case, to show the student how he may connect some or all of them to produce a combined capacitance of 60 microfarad and 15 microfarad. Okay, so you have 4 capacitors. You can use all or you can use some of them. So in your case, you want to have 20 microfarads. Sorry, you want to have 60 microfarads when one capacitor is only 20 microfarads. So you tend to want to increase your capacitance here. Because you want to increase your capacitance, this one here, the way to think about it is something like this. Because you want to have increased capacitance, you tend to want to have something like this, where C is C1 plus C2 plus C3, right? So the first thing you probably start is capacitance in parallel, okay? Because you see you're starting off from 20 and then you want to increase it to 60. The only way you can increase capacitance is by connecting it in parallel. So you try to connect it in parallel first. Say now you try to connect 3 capacitors in parallel. If you have 3 capacitors in parallel like this one is 20 microfarad, 20 microfarad, and 20 microfarad. You add them out like you would resistors in series. So 20 plus 20 plus 20 gives you 60 microfarad. Okay. Now when you draw your capacitors, it is just enough to draw the capacitor itself and then drawing something like this. Because sometimes students can draw it in this manner too, where they go and include the battery inside or cell inside. You need to say to draw something like this. Okay, you draw something like this with the cell included is also fine, but this entire section itself is actually unnecessary. You could have just drawn something like this as replacement. That one would be fine too. Okay, so this one is for this. Okay, and then the next one, you want to get a total capacitance of 15 microfarad. So how would you actually go and combine them? You will notice here that you are starting from 20 microfarad, and then now you somehow want to have a decrease in capacitance. So here, one of the things that you could probably see here is that you want to have decreased capacitance. The only way you can have decreased capacitance is if it's 1 over C1 plus 1 over C2 plus 1 over C3 power negative 1 and so on and so forth, right? So you need to connect your capacitors in series. That one will be the hint here. So how will you connect it? You could take your 3 capacitors from the one above, connect it in series with another capacitor. If you try to add them up, you will get 15. So let's just try and do this. Let me just try and simplify it for you. If this one is 20 microfarad, 20 microfarad, and 20 microfarad, this one can be simplified to something like this, where this one originally was 60 microfarad, and then this one is 20 microfarad. So this one is connected in series, isn't it? You add them like you would resistors in parallel. Sorry, you add them like you would resistors in parallel. That one will be this one here. Okay, 1 over 60 plus 1 over 20 power negative 1, giving you 15 microfarads. Okay. So again, same thing as before, just draw these terminals here and you are good to go. No need to draw the battery inside. Okay, so this one is for this. Okay, next one is page 8. Okay, page 8. So if you look at page 8, I'm just going to go through the first part for you. Page 8. Now, page 8, they ask you to define capacitance. This one, whatever I wrote here is actually wrong. Don't use this one. If they ask you to define capacitance, this one is actually asking you for a general definition of capacitance. The correct answer is actually just charge stored per unit potential difference. Okay. So charge stored per unit potential difference. This is the correct answer for that. You don't use the answer that I wrote here, the one where I say charge stored at one plate of capacitor per unit PD applied across the 2 plates of the capacitor. This is actually for your parallel plate capacitor. Okay, so this one, when they ask you for definition of capacitance, they're asking you for a general definition only, not for a specific definition for parallel plate capacitors. So the answer I wrote here is actually not really suitable. Okay, so don't use this one. And then after that, the other one here, you notice I say is ratio of charge to potential difference, right? This is actually not correct to say as ratio. It's charge stored per unit potential difference. Okay, so this two is wrong. Don't use that. Just use this one. It's from your notes. Okay, it's charge stored per unit potential difference under page 3, if I'm not mistaken. Okay, so you can actually just look at part C. Right, so part C, this is March 2016 P42. This one was page 8 of your worksheet, if I'm not mistaken. So if you look at C right now, what they mention is that you have a battery or EMF 12 volts and negligible internal resistance connected to a network of 2 capacitors and the resistors as shown. The capacitors have capacitances of 200 microfarad and 600 microfarad, and the switch has positions A and B. The switch is now moved to position A. Calculate the combined capacitance of the 2 capacitors, the charge on the 600 microfarad capacitor, as well as the potential difference across the 600 microfarad capacitor. So this one, usually for questions like this, it often helps if you try to draw out your circuit and try to simplify it step by step. So for example, when they tell you that your switch is moved to position A, it will be good to try and draw it out as it is first, and then try to simplify it step by step. So right now, if you're talking about at position A, this one should have been how your circuit looks like. Okay, so you had the 200 microfarad capacitor here, and then after that, this one is the 600 microfarad capacitor. Your PD, total PD is 12 volts. Okay, so at switch at position A, it's basically saying that you have one connection here like this, so that your entire circuit looks like this right now. Okay, so for this particular question, they ask you to find out the combined capacitance of the two capacitors. You can see that these two are connected in series. You would need to add the capacitances up like you would resistances in parallel. Okay, so basically the easy way to think of it is like this. When you're talking about capacitance and resistance, if it is in parallel, you do it like you would resistances in series. If it is in series, you do it like you would resistances in parallel. So right now, you have the capacitances connected in series, you treat it like you would resistances in parallel. So this one would be 1 over CT equals to 1 over 200 plus 1 over 600, giving you your final answer as 150 microfarad. Okay, then from there, they want you to find out the charge on the 600 microfarad capacitor. So let me just clear this thing up. So when they ask you to find out the charge on the 600 microfarad capacitor, one way in which you can do this is by first simplifying your circuit. So if you have this circuit originally and then you try to simplify it further, you become something like this. It can be approximated to just a single capacitor so that your circuit now looks like this. Okay, so you already found out that your capacitance, the total capacitance is 150 microfarad. This is still 12 volts. Now you imagine this right now for the circuit that has been simplified here. When you connect it like this, you probably would have an amount of charge that is being pushed to one plate of your capacitor, and then that same amount of charge will be pushed off the other plate of your capacitor. So the charge that is seemingly stored in your capacitor now is actually Q. Okay, this is the charge that will be released when you try to discharge it. The charge that is released is actually from one plate of your capacitor. It will flow through your circuit and then go to the other plate. This one was what I mentioned to you. This is the charge that is seemingly stored by your capacitor. They separated the charges, so there is positive and negative on one side. But then when you want to discharge it, the charge on one end is released so that it can flow back to the other end. Okay, this was the charge that people always think to be seemingly stored by your capacitor. Okay, so right now, your capacitor here stores a charge of Q based on this diagram. If you try to work it backwards, you could say that whatever charge that is flowing through here, whatever charge that is stored through this capacitor here, would actually also be the same charge that is stored in the 600 microfarad capacitor. Because you see your capacitors are connected in series, your charge Q here would be the charge Q stored in the 600 microfarad capacitor as well as the 200 microfarad capacitor, because you have a series connection right over here. Okay, so if you can find out what is your charge here for the 600 microfarad capacitor, is actually the same as the charge for this simplified circuit. If you want to find the charge for the 600 microfarad capacitor, it is the same as you finding the charge on this simplified circuit here. Okay, so how do you find the charge on this simplified circuit here? It becomes really easy because you know the capacitance and you know the PD across it. You can find out the charge stored. Because here, if you apply Kirchhoff's second law for this loop, there's only one source of PD and one source of EMF. Your EMF is 12 volts. Your source of PD here is the capacitor itself. It therefore must be 12 volts. Okay. So you apply equation C equals to Q over V. For this capacitor, you will be able to find out your charge. So over in this case here, C is equals to Q over V. This is actually for the whole circuit simplified. Okay. So you find out the charge that is stored in the capacitor for the simplified circuit. That charge is actually just going to be your capacitance 150 times 10 power minus 6 times your PD or 12. This one will be the charge. So this charge over here is the same as the charge in the 600 microfarad capacitor. Okay, so that's the understanding for this one. Now, the next part will ask you to find out the PD across the 600 microfarad capacitor. So in your current case, this one becomes easier also because you now know the capacitance of the 600 microfarad capacitor. You also know the charge that is stored on the 600 microfarad capacitor. You already found out that is 1.8 times 10 power minus 3. Okay, so you again would want to use C equals to Q over V applied to this capacitor itself to find out what is your V. So this one is for the 600 microfarad capacitor. This C equals to Q over V is applied for the 600 microfarad capacitor. So V is Q over C. The Q is 1.8 times 10 power minus 3. The capacitance is 600 microfarad. You do your workings accordingly. You will get the voltage as 3 volts. Okay. So this one is the proper way to do this question. Because sometimes when people look at this question here and they see find out the PD across the 600 microfarad capacitor, they are so used to doing potential divider from your AS that they will say that the voltage here, I can use potential divider equation where I say that V is equals to 600 over 600 plus 200 times 12. So the answer you get by doing this is actually going to be 600 over 800 times with 12. You're going to get 9 volts. You see, the answer is different than what you found here. So this one is actually wrong. Okay, so don't use potential divider equation. Okay, now then if you move on to number 2, the switch is now moved to position B. Just let me erase all certain stuff here. Your switch is now moved to position B. Calculate the potential difference across the 600 microfarad capacitor when it's discharged 50% of its initial energy. Okay, so this one I'll just show you a ratio method here just for the workings here. Because you're talking about energy here, you know the energy of your capacitor can be given by 3 different equations. Is half QV or half CV squared or half Q squared over C. All right. So what is the equation that you would want to use here? Which one is the suitable one? They need you to calculate PD. So anything without PD is going to be out. That means the third equation is out. That leaves you with only the first two that you can consider because they have PD. This is what you want to find. So between these two, which one do you want to use? You would try to use the second one because here your capacitance is fixed or constant. The last lesson I mentioned to you that when you have a certain capacitor inside the circuit, its capacitance value will not just simply change, it will remain fixed. But the charge stored or the PD across it can actually change. Okay, so in my case, even though my capacitor right now, the circuit it was in has the switch position changed from A to B, the capacitor itself was not changed. Its capacitance value should still be the same. Okay, but when it loses its energy now, although your capacitance value does not change, your charge stored will change. So if you look at the first equation here, this Q here will actually change. And not to mention your V is also changing. You have two unknowns here that are changing. So you will not use the first equation. you will only use the second one because it has only one changing variable, which is the PD that you are trying to find. And then the other variable here is fixed or constant. You can easily use ratio method here. So if in my case, I say that C is constant, E will be proportional to V squared. So that E2 to E1 is equals to V2 squared to V1 squared. So E2, I know is half of E1 because you see they say that you've lost 50% of your initial energy. That would have told you that E2 is now half of E1. So this one is half E1 over E1 equals to V2 squared over V1 squared. So your initial voltage V1 should be 3 volts because you see when you are switching from position A to position B, at position A you were talking about this, your 600 microfarad capacitor, you calculated the voltage across it as 3 volts. You already calculated the voltage across your 600 microfarad as 3 volts. This one was your capacitor 600 microfarad at position A. It is already charged to 3 volts. So when you switch to position B and is discharging its energy, the voltage would now drop. That is your V2 that you want to find out. Okay, so your V1 being 3 volts, this is what you expect to see. So your E1s will cancel off. V2 squared is therefore going to be 3 over 2 volts. Sorry, it's going to be 3 over 2. And then after that, V2 is definitely going to be square root of 3 over 2. You will get your answer as, oh wait, sorry, I forgot to square this one, my mistake. This one is square, this one is square. So you find out your V2 by square rooting this expression here. It's going to be square root of 9 over 2. You're going to get the answer as 2.12 volts. Okay, right. So at switch in position B, I forgot to kind of draw it out for you. At position B, your switch is actually at this current position. Okay, so that your circuit now looks like this. Your 600 microfarad capacitor is actually discharging, because if I try to draw your circuit at switch position B, this is what is actually happening now. Okay, you are no longer connected to your voltage supply. Your capacitor here, the 600 microfarad, is now directly connected to a capacitor, to a resistor. It will actually now discharge. Okay, so that's why here just now, when you suddenly switch to position B, this 600 microfarad capacitor, it was fully charged. It will now go through discharging. But when it was fully charged itself, your PD was 3 volts, because that is what you found here. So once it has discharged to 50% of its energy remaining, you're trying to find out what is the new PD here. That one is 2.12 volts. Okay, so that is for page 8 of your worksheet. Then if you're okay with that, let me just move on to the next one. Next one should be page 39, if I'm not mistaken. Okay, next one is page 39. Okay, now explain what is meant by the capacitance of a parallel plate capacitor. This one, as I mentioned, the moment they mention to you to define the capacitance of a parallel plate capacitor, your definition needs to be a bit more specific, in the sense that you have to word it in this way. The charge stored on one plate of one capacitor, the charge stored on one plate of the capacitor per unit PD applied across the plates of the capacitor. Okay, so this is one. And then after that, if you look at part B, you have 3 parallel plate capacitors that each have a capacitance of 6 microfarad. Draw circuit diagrams, one in each case, to show how the capacitors may be connected together to give you a combined capacitance of 9 microfarads and 4 microfarads. Okay, so here the question already told you that you have 3 capacitors. How are you going to connect those 3 to give you your combined capacitance of 9 microfarad and 4 microfarads? So this one is through trial and error. For the 9 microfarads one, you could have just connected it in this way. This one I'll just draw it on the left hand side. You could have just connected it in this way, where you have the first 2 connected in series, and then they are then connected in parallel to the third one, like this. Okay. Usually when you draw your circuit connections for capacitors to give you a certain combined capacitance, for questions like this, it is just sufficient for you just to draw the capacitors and then the terminals like this. In my working here, I actually drew it connected to a power supply. This portion here is actually not really required to be drawn. You can make your life simpler and your workings neater by just drawing something like this. That one would just be sufficient. So for this one, how do I know it's going to be 9 microfarad? You kind of need to simplify one by one. So say in my case, this one was 6 microfarad, 6 microfarads, and then this one was also 6 microfarad. I simplify the series connection first. This one I would need to add it like I would resistances in parallel. They're always in the opposite direction, they're always in the opposite manner. So this one will become something like this now. This one is actually the capacitance in series, which was 1/6 plus 1/6 power -1, giving me 3 microfarads. Okay, so this is 3 microfarad. And then this one here is 6 microfarad. So because this is connected in parallel now, I need to add that like I would resistances in series. So C total here is just going to be 3 plus 6, giving me 9 microfarad. Okay, so just like that. And then as for the 4 microfarad one, what you just need to do is you connect the first 2 capacitors in parallel, then connect the third one in series. So if I connect it like that, this is what I expect to see. You will get 6 microfarads here. So you will get 6 microfarad here, 6 microfarad here, and then 6 microfarad here. We'll first try to simplify the parallel connection first. If you simplify the parallel connection first, you add it like you would resistances in series, so that this one is going to be 12 microfarad. Because this one, I can say that the capacitance in parallel was actually 6 plus 6, giving me 12 microfarad. So this one is in turn connected to another capacitor of 6 microfarad. Because this is now connected in series, I add the capacitance up like I would resistances in parallel. So this one is 1/12 plus 1/6, power -1, giving me 4 microfarads. Okay, so this is the proper way to connect your capacitors. You have to do something like try and error. Sometimes you connect them in series, sometimes you connect them in parallel. Okay, so this one, let me just clear the diagram off. So in part C, you want to find out a certain thing from this diagram where they tell you that 2 capacitors or capacitances, 3 microfarad and 2 microfarads are connected in series with a battery of EMF 8 volts as shown in this figure here. Then after that, calculate the combined capacitance of the capacitors. This one, maybe it's better if I just try and redraw your diagram here. This one is something that looks like this. So this is 3 microfarad. This is 2 microfarad, and then this is 8 volts. So find out the combined capacitance of the two capacitors. These are connected in series. You add them like you would resistors in parallel. So it's 1 over CT equals to 1 over 3 plus 1 over 2. This is actually the same as you writing this. Sometimes you will notice that I tend to write it in bracket with power -1. It's actually the same thing as writing this. Okay. So your total capacitance will be 1.2 microfarads. All right. And then if you look at part 2, use the answer that you have found to determine for the capacitor of capacitance 3 microfarad the charge on one plate of the capacitor. Okay, so when they say charge on one plate of the capacitor, it's actually really talking about the charge that is seemingly stored by the capacitor itself. Okay, so here the 3 microfarad is this one. The easy way to do this is to again simplify your circuit. I can simplify those two capacitors as a single capacitor, where it is now something that looks like this. Okay, so you already found out the capacitance value here is 1.2 microfarad. Okay, so right now, if you want to find out the charge on one plate of the capacitor, this one you can think of it as I'm pushing an amount of charge Q here. That same charge Q will be deposited on one plate of your capacitor. That same amount of charge Q will be repelled off the other plate of the capacitor. So that goes to the other capacitor plate here. And then that same charge is also again repelled off the other plate. So that whole charge now moves like this. When you're talking about the charge stored on one plate of the capacitor, it's really talking about this charge itself. Okay. So to find this charge, it'll be easier again to look at it from a simplified diagram like the ones that has just been drawn here. This one, I know that it will push an amount of charge Q out so that it gets deposited on this left plate here, and then that same amount of charge Q will be repelled off the other plate. Okay, so this Q is the same as the Q above. If you can find this Q, you will be able to solve this question. So you again apply C equals to Q over V here, but applied for this capacitor here. So right now, you notice that you know the capacitance value. It is 1.2 microfarad. And at the same time, you also know the PD across it because here your voltage supply was 8 volts. According to Kirchhoff's second law, this one will also be 8 volts. So you know the voltage, you know the capacitance, you can then find out what is your Q. So you apply C equals to QB here for the whole circuit simplified. This one is for the whole circuit simplified. Okay, so Q is CB here. Use the total capacitance, multiply with your total PD, you get your total charge as 9.6 times 10 power minus 6 coulomb. Change it to microcoulomb, you get 9.6 microcoulomb itself, just like that. Okay, so that is okay. And for that same 300 for that same 3 microfarad capacitor, find out the energy that has been stored by the capacitor itself. This one, because you know the charge and you also know the capacitance, you could straight away use E is half Q squared over C. Your charge is 9.6 microcoulomb, change it to coulomb, square it, divide by your capacitance, 23 microfarad, multiply with half, you're going to get 1.54 times 10 power minus 5 joules. You cannot use any of the energy equations with voltage here because you do not know what is the voltage across here. Okay, because E is half QB, E is half CV squared, E is half Q squared over C. You already found out your charge as 9.6 microcoulomb. You already know your capacitance is 3 microfarad, but you just do not know your voltage. You cannot say your voltage here is 8 volts, because if you look at this diagram here, there are two capacitors. The total PD of these two capacitors will be equals to 8 volts. But the PD of the 3 microfarad capacitor itself is unknown. So you do not want to use any of the equations with phi inside. You want to use this instead. Okay, so that is for this particular question.